Okay, that means it's going to rain. I agree. Okay, and what rain is basically liquid water. Honestly, with 100% relative humidity, something's going to happen to that water vapor. It's going to go from a gas to either a liquid, and you're going to see it in the form of fog or clouds, or it's going to go from a gas to a solid. What's frost? It's water vapor going from a vapor to a solid. Isn't that wonderful? It's so beautiful.
It's annoying.
It's pretty.
Not as pretty as it is annoying.
It's not that pretty in the morning.
That's true.
When you gotta go.
When you have to scrape it off.
Yeah.
It's still pretty. Anyway, so you guys have been recording relative humidity, but and it's the water in the air. But actually, all of these are ways to express water vapor in the atmosphere. And we're going to pick these apart. Anybody numbers people in here? Numbers people? No. Okay. Well, we're going to kind of think, I'm not going to make you do calculations, but you have to kind of think quantities. I'll show you what I mean. So each one of these are a little different. I'm not going to slow that down. Okay. I just, up here, in case you're wondering, I was going to ask you guys. Okay. So in the wintertime, do you run a humidifier or dehumidifier?
Humidifier.
Humidifier, exactly. In the wintertime, the air can be really dry in your houses. So actually that corresponds to this one right here. It's got ice cubes, okay? And for each one of these, I don't care about the liquid, so stop looking at the liquid. I care about that air above the liquid at different temperatures. So you would think this is pretty dry, and you're right. But I might convince you maybe not, but at this temperature, it might be, one way to express the humidity is like 80% humidity, relative humidity, but at that temperature, another way to express the humidity might see it's the absolute or the mixing ratio is very low. Okay? All right. So in the summertime, you do a dehumidifier, right? Okay. If you've ever heard the adage, and I hate to even say it, but warm air holds more water vapor. Okay, that's what we're going to be talking about. And it's not that the air holds more gas, water vapor, but it kind of ends up that way. So I have 3 different temperatures: cold, medium, and hot. Okay, so water in the air, water in the atmosphere. Different ways to express that. And yes, these usually make it to my exam in one form or the other. Okay, so are you familiar with the ratio? Basically dividing, you take the first number and you take that number and you divide it into the number at the bottom. Okay, that's a ratio. So one way, both of these ways basically take a parcel of air, and you're going to see it on the next slide, a circle of air. And in that circle of air, you somehow get to the mass of the water in grams, and you get to the volume of that parcel of air, okay, and you divide it out. Okay, that's called absolute humidity. Okay. So, note that in the bottom is the volume of the air. So we're going to talk about chunks of air that actually, they don't stay one volume, they expand. Do you guys remember the weather balloon that went up? Do you remember how big the weather balloon would get?
Big as a house.
As big as a house, exactly. And chunks of air that go up do that too. So if you have a chunk of air that's expanding, basically that bottom term is getting larger. Okay, so this will actually change with volume, but with temperature, it shouldn't change. Okay, so that's absolute humidity. And try to find the difference between absolute humidity and mixing ratio. What they both have in common, what's the difference?
Mass.
The mass, exactly. The mass, over here, instead of taking volume of air, you take mass of dry air. Okay, instead of volume. But what do they have in common?
Mass of the water.
Mm-hmm. Oh, sorry. Oh, you're fine. Okay. So this one down here, the fact that it doesn't use volume in the bottom, it will not change when your chunk of air rises and gets big. Okay, so mixing ratio is kind of a nice, more of a kind of constant thing. Mixing ratio says, hey, I just got this chunk of air, it's got this mass of dry air, I'm going to put that in the bottom. In the top, I'm going to put the mass of the water that's there. Okay, so that's two ways of saying how much water vapor there is in a chunk of air. So here's your chunk of air, cute little Mickey Mouse water molecules. You know they're gas because they're buzzing around. Can you see that movement? As much as they can, a little whoosh. Okay. So that isolated chunk of air, they said they got 20 grams of water vapor, and they have a volume of 1 cubic meter. So they can go ahead and knock out the absolute humidity. All they got to do is divide the 20 grams by the 1 cubic meter. Okay, so that is the absolute humidity. For the same chunk of air, if they go ahead and find out the mass of the dry air, then they can get to the mixing ratio. So the mixing ratio is that same 20 grams of water vapor divided by the dry air, which is 1 kilogram. Okay, so that's it. So we're going to actually revisit this slide. Yes, as big as a house. So when balloons or anything goes up, basically it expands because the air is thinner up there, there's less pressure, and that's what things do when they're given less pressure. It's kind of like your ears popping. Okay, they get bigger. So there it is, getting bigger. And so as it gets bigger, though, like I said, the mixing ratio won't change, the other one will change. So let's just say that no water vapor was lost or gained. Let's say its new volume is twice of what it was before. So now its new absolute humidity is different. It's what? A half of what it was before, right? Because now you take the 20 grams of water vapor divided by now the 2 cubic meters. Okay? So that's 20 grams per cubic meter. Mixing ratio should be the same. And it is. Okay? So two other ways of expressing water vapor in the air. That's important to the upcoming discussion. All right. So for your Unit 1 exam, one of the things on your review sheets is what is the composition? What in this room, what's the most abundant gas?
Nitrogen.
It is nitrogen. Very good. Nitrogen on here are red. Okay. What is the next abundant gas?
Oxygen.
It is oxygen. Oxygen are green. Perfect. And of course, Mickey Mouse are water vapor. Okay. So one of the things that scientists have realized is that you can have a gas mixture. Okay. This is a gas mixture in here. It's same throughout pretty much. 80-20 nitrogen, oxygen with a smidgen of water vapor.
I have a question. Are you red, green, colorblind?
Am I what?
Red, green, colorblind?
Why did I mix those up?
Yes.
Okay. Not usually. The red are, yeah, because the oxygens need to be red because they're part of the water molecule. Yes. So no. Thanks for asking though. But if you take 3 gases like this and you put them in the same container, like they're in this room, okay, they basically will intermingle and they'll all 3 be pounding around, bouncing around. So when you guys on your weather logs are recording pressure, atmospheric pressure, yours are probably in inches of mercury, but basically they're gas pressure. And I'll try to talk about how do we get it into inches of mercury later. But gas pressure, okay, and they all work together. We have what we call a partial pressure of nitrogen, a partial pressure of oxygen, and partial pressure of water vapor, and they make the total pressure. Okay. So if you're into equations, which you don't necessarily, but I said PT is the total pressure, is equal to the pressure exerted by all those gases. Oops. It's cool. It's a neat sort of thing. Okay. Now, I don't know, can you guys see like what's happening on the side of this glass up here? What is that?
Condensation.
It is condensation. Perfect. So honestly, we talked about 100% relative humidity. Also, honestly, inside there, that air in there is 100% relative humidity. It's condensing. Exactly. So we're going to talk about evaporation, condensation, and saturation. We would say here, anytime somebody says 100% relative humidity, the air is saturated. They mean the same thing. And I think I have a slide coming up to say that. So that air is saturated with regard to water vapor. Okay. So you're going to see on the next slide, basically these covered, I like it, but just to kind of give you a preview. Basically, choose green. This is my water down here and like my watch glass here. Of course, if I put an up arrow from liquid to gas, what would you call that?
Evaporation.
Me too. And then if I put an down arrow, what would you call that? Condensation, exactly. And if we use the arrow to say how much of evaporation, how much condensation is going on, if you use those arrows to make them equal, then that is actually, we say that system is at equilibrium. Equal evaporation, equal condensation. Hi, Matt. Okay. So it's at equilibrium. You think this one's at equilibrium?
Yes.
I do. This one's room temperature. Hard to tell. It has. You think though, if we left it covered for like overnight, maybe it would become, the air would become saturated. We'd get it at equilibrium. I think quite possibly. Okay. Yes, exactly. Okay. So one of the things I like about these figures, I picked out this book because I like what your author does with figures. So this is the chamber of water at the bottom. They kind of started with nothing in the headspace above there, okay? And keep an eye on the pressure gauge. So a little bit ago, I showed you that circle with the nitrogen and the oxygen and the water molecules bumping around. Okay, so that pressure gauge is going to read that pressure. All right, so given a little bit of time, okay, we see both evaporation and condensation, but I like what your author did. Which is doing more, evaporation or condensation there?
Evaporation.
Yeah. More evaporation than condensation. Is it at equilibrium? No. Is it saturated? Not yet. Then, oh, by the way, check out the pressure gauge. Isn't that adorable? It's flicking, right? So you give a little bit more time, and now what would you say about the rates of evaporation and condensation?
They are the same.
They are the same. It's at equilibrium. The air is saturated. 100% relative humidity. It's going to storm. No, it's going to rain. It's all muggy in there, okay? So kind of terms that we've talked about are evaporation and condensation. These are things that you already knew. Evaporation, condensation. Saturated air. Okay. So the vapor pressure, or saturation pressure, would be that cute little knob up here at the top. This thing, okay, that actually is showing you the vapor pressure in that headspace above that liquid. The more the deflection, the greater the pressure in there. Okay, so only that last one is the saturation vapor pressure. Why? Because evaporation is equal to condensation. It just is. Okay. So we can make what? We can make a headspace saturated, like that. Okay. So we actually are going to focus mostly on that mixture we saw with the nitrogen, the oxygen. See, the nitrogen was green, the O2 molecules are red, and the H2O molecules are Mickey Mouse. So all three of them floating around in the common circle together. We're really going to just focus on the water vapor and kind of talk about that pressure that the water vapor exerts. But whether you're talking about nitrogen gas or oxygen gas or water vapor, you can go ahead and bump up the pressure in one of two ways, and it kind of makes sense. I like things that make sense. Okay. One of the ways you can do it, does this make sense? Because we talked about all matter has motion. What happens if we go ahead and take a gas and crank up its temperature? What happens to its motion?
Speeds up.
It speeds up, exactly. And actually the impact it has on its container or the little device measuring pressure, so its pressure goes up. So if you increase the temperature, it will automatically increase the pressure. Increase the temperature, you'll increase the pressure. And again, it goes back to that kinetic energy, okay? If you lower the pressure, lower the temperature, they will go slower and actually lower the pressure, the vapor pressure of that gas. Kind of reminds me of buying ants in the mail. Send them to you and they're frozen. Anyway. Okay, here's another thing you can do. What happens if you take a jar or something, and what happens if you shove more gas particles in there? What's going to happen to the pressure? It's going to go up. Yeah. It makes sense. Exactly. So that would be changing the amount. Okay? So if you increase the water vapor, the water gas particles in there, okay, your vapor pressure is going to increase. If you take some water vapor out, which you can do by maybe condensation or removing them, okay, then that's going to decrease your water vapor pressure. So they kind of make sense. All right then. See, looks like saturation, right? Evaporation, condensation, it's like a tug of war. Okay. So this says saturation vapor pressures increase with temperature. So 20 degrees Celsius, 30 degrees Celsius. Check that second chamber. Is it at equilibrium? Count the particles. I got 7 and 7. So it's evaporating and condensing. Anytime you see that, to kind of emphasize what I'm trying to, the point I'm trying to make here, is think 100% RH. In both of those cases. But check out the pressure gauge. Okay. Next thinking. Are you just kind of, let me know if you have a question.
Did you hand out the PowerPoint for this one?
No, they're available though. And if you ever get in the deal where you don't have the PowerPoints to write them in, if you let me know, I can make arrangements to get those to you for those slides.
I never get on college websites.
Okay, but you can eventually access the, okay, but let me know if you need to.
I'll get them printed off.
Okay. So that second scenario, the pressure increased for 2 reasons. There's more water vapor, okay, higher temperature. The newly established equilibrium ends up with more water vapor up here, okay? So more particles. But the other thing is they have more kinetic energy. So it's like a double whammy, okay? So I guess I go back to this, right? Okay, these guys in here, actually, let's just assume we let it go for 48 hours or something. And we went ahead and sealed it up, and I saturated the headspace above each one of these liquids. Okay, we're at equilibrium. Wouldn't these be like moving really slow? There wouldn't be very many of them in the cold temperature. And these up here, really fast and one of them. Okay. All right. So this blue line is kind of the sweet mark, the sweet point at these temperatures at which the mixing ratio is such that it's saturated. Okay, so they're picking on a temperature of, looks like 14 degrees. Well, sorry, not 14 degrees. They're picking on a temperature of 20 degrees. If you want to have 100% relative humidity, then your mixing ratio, needs to be 14. 14 grams of water vapor, H2O gas, per 1 kilogram of dry air. Okay, then your air, then it's saturated.
Do we need another equation?
What's that?
Will we need to know that equation?
We talked about different types of, talking about humidity, and mixing ratio is one of them. Yeah, so this is mixing ratio. And it's the mass of the water, gas, or water vapor per 1 kilogram of dry air. In this case, it's 14. But the point is if we go to, instead of 20 degrees, we're about, we're room temperature here. Let's say, well, what is this one? Well, it's saying it's above 100 degrees, which really kind of freaks me out. But let's just go with 35. Okay, pick on 35. So at 35 degrees Celsius, okay, go up here, and we see that at saturation, okay, this actually is the amount of water that temperature. Have you ever heard warm air can hold more water? That's kind of what we have going on here. At warm temperatures, there's more, the saturation amount is more in terms of mixing ratio. Let's finish that thought. To me, it kind of looks like 34 grams of water vapor, water gas, per 1 kilogram of dry air. This, and that would be very warm, 35 degrees Celsius, that would be a terribly warm house. This is why you run the dehumidifier. Okay. Right. Okay. So let's pick on a few scenarios. Not these scenarios, not these temperatures necessarily, but these temperatures on that curve back there, or if the curve didn't hold them, this is what they would be on that curve. This actually is the saturation mixing ratio. Let's see, Celsius we picked on. So the Celsius is without the brackets, so we picked on 35. Mixing ratio of 35, is that right? 35, yeah, nope. I'm going to pick on 35 and 35. 35. Yeah, I buy that. I said 34, but that's okay. That's just weird, 35 and 35. Okay, so this is the temperature, and this is the saturation mixing ratio. So you increase the temperature, you increase the amount of water it can hold at that temperature, basically. So we're going to pick on temperature 25 degrees Celsius in the next table, or the next few figures. 25 degrees Celsius, 77 Fahrenheit. This would be the point where your air is saturated. 20 grams of water vapor in 1 kilogram of dry air. Okay, oops, coming up. But before we do that, let's talk about the one that you guys have been recording. If you're doing a weather log, you've been recording this one, percent relative humidity. So basically, as you know, the closer you are to 100% RH, relative humidity, what you've been recording, the closer you are there, the closer you are to some sort of condensation event, whether that's rain or fog or snow. So 100% relative humidity means basically that water's going to come out of its gaseous state and do something. So this is how they calculate the RHs, the percent RHs. Basically, they take the amount of water content in the air, and they divide that by the amount of water content that would be required at saturation. Okay, so there's this, and the one down at the bottom, the water required for saturation is dependent upon temperature. That's a table thing. So sometimes I tell students, and I'm sure this makes sense to you, this comes from a table. And this comes from your gizmo, from measuring. Okay, now back to the 25 degrees Celsius. Okay, so 25 degrees Celsius, they kind of have the temperature at the top there. Notice that conveniently, it's got 1 kilogram of dry air in there, which makes life a little bit easier. So they go ahead and they say, right now there's 5 grams of water vapor in there. So here are kind of the stats that go along with that flask. Notice the table a little bit ago, I said at this temperature, we can bump it up to 20 grams for 1 kilogram of dry air, and we're fine. We're at 5. So we have a ways to go, right? So this is actually not saturated. And with regard to the RH, the percent RH, we could find that by taking the 5 and dividing by the 20. Does that make sense? 5 is what we got, 20 is what we can hold at that temperature. All right. So maybe let it set a little while. Let evaporation do its trick. Now instead of 5, we got 10. Okay? So the same temperature, so that means that on the table, this number comes from the table, the saturation amount, still 20 grams, we only got 10, so we're undersaturated. So actually, the percent relative humidity is that 10 divided by 20, what it can hold. Your RH would be 50%. The last one, I bet you maybe figure, is we basically let it saturate, equilibrate. Let it basically, the rate of evaporation is equal to the rate of condensation. There might be condensation on the edges there. So here finally we've got 20 grams there. At that temperature it can hold only 20 grams. Okay, so 20 divided by 20, you have reached 100% relative humidity. Okay, so percent humidity is another way to express how much water vapor there is. Humidity is general, okay? RH is kind of specific like this. Because we talked about the mixing ratio and the absolute humidity too. You're like, oh, goodness gracious. All right. So times when you reach 100% relative humidity, maybe by accident, maybe not, okay? If you're taking a shower and you get out and it's all steamy, okay, think of that steam as just like what I've been talking about, fog and a cloud. You can see it, basically water is condensing. It's like little aerosol particles in your shower. They're kind of fun. Have you ever just kind of stood there and kind of watched the, either fog or in your shower, kind of watch the particles fall? Because gravity will work at them. They're kind of just slowly falling down. Fog is really cool if you just look at the particles. It's like, oh my gosh. When you see your breath on a cold winter day, okay, which is not good, but basically that fog you're creating is your own moisture or vapor, water vapor condensing. That's kind of fun. And one of my favorite, I guess, is, have you guys ever been to Adventureland? Okay. Or a theme park? They've got a lot of black asphalt in Adventureland. I don't know if all theme parks do that. You're like, dude, why'd you choose black? I don't know. But sometimes we're there when the sun's out and you get a quick shower and then the sun comes out again. And actually, hot pavement, rainfall, we call this actually frontal fog. And we kind of see the wisps of smoke coming up. Okay, that is actually a water vapor that is condensing. Okay, so let's pick on another aspect. Can't remember what this is. We're going to look at 3 temperatures. Okay, 20 degrees Celsius, 10 degrees, so we're going to cool from left to right. You see 3 little flasks. 20 degrees Celsius flask, a 10 degrees Celsius flask, and a 0 degrees Celsius flask. Now, one of the things we know is we get cooler from left to right here in a minute, that actually the amount to reach saturation goes down. Okay? So at 20 degrees, we can hold 4 grams of water vapor for every kilogram dry air versus 7 grams of water vapor at 10 degrees versus 3.5 degrees of water vapor at 0 degrees. All right. So here we go. So here we have the first scenario, and kind of all that statistic stuff is down here for us to see. From the table, that's what this number 1 is. That's from the table. That's the saturation amount. In this scenario, we're running 7 grams. 7 grams of water vapor in this scenario. So RH, percent RH, would be 7 divided by 14, or 50%. All right, cooling her down. So we cool it down, and on the table you saw now at 10 degrees, I can only hold 7 grams of water vapor per 1 kilogram of dry air. Wow, I can hold 7, and I got 7. Okay, so 7 divided by 7, you are at 100% relative humidity there. Doing the halls. But you know what? One of the custodians, I don't know if you know that, they're really nice, but his wife is this close to giving birth. So, look, do what you got to do and get out of here. So, anyway, so we said the last one's going to be 0. Look at the puddle there. Okay, so it had 7 grams. Okay, but at that lower temperature, it can only hold 3.5 grams. So you see what happened? It rained. Okay. We didn't want to be super saturated. Does that make sense? I like that. Like I said, I think I like these examples. All right. So bottom line, okay, if your goal is to get fog, if your goal, which is basically condensed water, or if your goal is to get clouds, which is condensed water, okay, you need to hit that 100% relative humidity. You need to saturate the air. And you can do that one of 2 ways. Both of these ways go to getting closer to saturated air. You can make it cooler, like we saw a minute ago, okay? Or you can increase the water vapor. Let me see this link, this blue link. Some videos here. I didn't test it out ahead of time, so I don't know. We shall see. Just kind of, I feel like, reiterates what we've been talking about. That if you want to change the relative humidity, pushing for that 100% relative humidity, you're trying to jack it down, right? You don't want all this humidity. You can monkey with the temperature, okay? And here's the consequences with the temperature. You decrease the temperature, you'll increase your relative humidity. You increase the temperature, you'll decrease your relative humidity, okay? Or you can change the number of water vapor particles there are floating around to get saturation. So here in a minute, I have basically kind of to show you what's the warmest part of the day. We talked about this in
4 o'clock.
2, 3, 4 o'clock exactly. That's what we call the lag of maximum. That's also on your test for next week. The lag of maximum. And that's on a sunny day, you know. So when's the coldest time? Right before dawn, that's right. You're camping, you're like, oh my gosh, is this night ever going to be over? Right before dawn, exactly. That's the coldest time. So with that in mind, the chart you're going to see here in a minute, kind of keep that in mind. I think there still might be a homework question on this for Chapter 4. But basically, at those low temperatures, okay, at dawn, you actually have your highest relative humidity. And it might not seem like it, but haven't you ever, like, if you're camping again, everything's all wet and everything, you're like, oh my gosh.
Use
Okay.
everywhere, yeah, makes sense.
Yeah. And so you guys told me the peak times are like 3 to 4 p.m. or so. I agree. Increase the temperature, you decrease relative humidity. So it's weird to think, you know, you're out there, you're like, dang, it's so hot. But honestly, remember that at those higher temperatures, that warmer air can hold more water vapor. So your relative humidity is actually gone down. Does that make sense? Okay. I know it doesn't feel like it, but that's the deal. So these are the graphs I was telling you about. The top one is the temperature. And you can see this kind of, this peak here. I better choose a different color. Peak here. Looks like they're talking about 5 p.m. or so. Okay. So the peak temperature actually is the minimum RH. Okay. Now this is assuming that you don't have any extra water being added to the atmosphere. What the water in the atmosphere you have is what you keep. All right. So, I can't remember, your weather logs, are you recording dew point temperatures?
Yeah, I think so.
Okay, I don't know. So I'm gonna play a video before break, but, and we're about ready for a break. Yeah, this is good. Cool. But the dew point temperature is the temperature you need to jack it down to in order to go ahead and reach 100% relative humidity, to reach saturation, okay? So that's what those temperatures are. Let's see. 16 degrees. The feels like temperature, do you guys see the dew point temperature?
It's right below the 16.
Oh, that's the feels like is 8, yeah, with the wind, exactly. We could pull up that wind chill chart and plug in the 16 and the 5 and come up with 8 for feels like. Let's see, dew point temperature. I'm hoping current details will give us that. Yeah. So dew point temperature from 16 is 3. Okay, so dew point temperatures are always going to be lower than what they are now. Because basically you got to go down. Sometimes they'll talk about the dew point depression, and so that would be what, 16 minus 3. So it's 13. 13 degrees is what you got to go. So probably no fog tomorrow. Does that make sense? Because you're like, the odds of dropping that is not very good.
That's good. Golden Spring.
What's that?
That's good. Golden Spring.
You should be just fine. In the morning?
Yeah. What was it?
Okay.
Yesterday I was on the road to Atumwa at 8:30, so that was fun.
Oh, that's not good. Yeah.
I was back by 2. Wasn't that bad.
Very good. So, did you guys catch the relative humidity a minute ago? What did it say?
43%, I think.
43%. Very good. So, the fact we have to go 13 degrees means the relative humidity is kind of low, 43%. If our current temperature was near the dew point temperature, our relative humidity would be really high. Does that make sense? I think so. This actually is the poor man's way, who doesn't have a measuring device, to see how humid it is. Okay? So basically you have a cold beverage, and if it sweats, okay, if it sweats, then that means basically it's reaching the dew point temperature around that container. Actually, I don't know how long it took me. I don't think it took me that long. But you guys know when a glass sweats or something, there's not liquid going through the glass. Basically, it's water vapor depositing onto your container. Yeah. So I just really think that there could be some science there, you know. Dry heat, right? Like if you go to Arizona, do their things sweat? I doubt it. Low humidity? I don't know. So just to kind of finish that thought, here are some kind of statistics from dry air to lower to moist air. You know, if it's really dry, if it's really dry, well, this might not mean it's really dry, but if you have to jack the temperature down 10 degrees, then probably it's not going to precipitate, and that would be snow. If your humidity is greater than if you only have to lower it to 55 degrees Fahrenheit, then that means you're warmer than 55, doesn't it? Right? And so, it's relatively humid. Under humid conditions are when we get our cool thunderstorms. We'll be talking about that. You definitely need moist air to form those. If you have a dew point temperature that's 65, again, you're warmer than that, and you're probably not very comfortable. In the tropics, their dew point temperatures run kind of ongoing 70 or greater. Okay, and dew point temperatures of 75 are just terrible. So let's take another break, 10-ish minutes or so, and come back. Friday.
Emergency review for